We're going to take a look at another convergence test for series. This time we're going to examine what we know about series when we compare them to integrals that we either know converge or diverge. In order to understand how we can use the integral test to evaluate whether or not a particular series converges or diverges, we need to start with a few assumptions. First, we have some series, the sum from n equals 1 to infinity of a sub n. The terms of that series, a sub n, correspond to some function so that f of n is equal to a sub n. F of n has a real valued version, f of x, and that function f of x is continuous, positive, and decreasing for x greater than or equal to 1. With those ideas in mind, let's take a look at a couple of graphs. In our first graph, given our sequence a sub n, on this graph, the points we're highlighting represent the points n, a sub n. In other words, this point right here is 1, a sub 1. This point right over here is the point 2, a sub 2, and so on and so forth. When we look at this graph and we consider the rectangles that are drawn on it, notice that each of the rectangles has a base width of 1. Each of the rectangles has a height that corresponds to its term in our given sequence or series. This height is a sub 1. This height is a sub 2, and so on and so forth. Given the base of 1 and a height equal to the nth term, the area of each rectangle is then a sub n times 1, or just a sub n. So our areas are a1, a2, a3, and so on and so forth. In other words, the area on this graph exactly represents, if we imagine that this continues on infinitely, this represents the sum from n equals 1 to infinity of a sub n, summing up the areas that we have here. Our next graph is very similar. It's a slightly different representation. So here our right endpoints represent our sequence value. In other words, this point right here is the point 2, a sub 2. This point is 3, a sub 3, just as in our other graph. But now notice, while our rectangles still have bases of 1, their heights are given by their right-hand endpoints, so that the area of the first square is a sub 2, the area of the second square is a sub 3, and so on and so forth. We can then see that our area here represents the sum from n equals 2 to infinity of a sub n. Our last graph here represents our function f of x, and here we can see that the area is going to be equal. Again, we're assuming it continues on infinitely to the right with our continuous positive decreasing function. The area is the integral from 1 to infinity of f of x dx. Let's take a look now at these three areas we just visualized in comparison to each other. First, we have our blue area, which represented the series, the sum from n equals 1 to infinity of a sub n. On top of that, we have our function's integral, the integral from 1 to infinity of f of x. On top of that, we then have the series starting at 2, the sum from n equals 2 to infinity of a sub n. It's easy to see here that we can draw some comparisons between these three quantities. We can see that the sum from n equals 2 to infinity of a sub n is less than or equal to the integral from 1 to infinity of f of x, which is then less than or equal to the sum from n equals 1 to infinity of a sub n. This string of inequalities allows us to draw some conclusions about the convergence of the series based on what we know about the convergence of the integral. We need to understand one more idea before we state what the theorem tells us. That idea is that the sum from n equals 2 to infinity of a sub n and the sum from n equals 1 to infinity of a sub n either both converge or both diverge. The only difference between the two of them is one single term, a sub 1. That is a finite number. Therefore, if the sum from n equals 2 to infinity of a sub n converges to a finite number, adding on an additional finite number in the sum from n equals 1 to infinity of a sub n won't change that fact. Similarly, if the sum from n equals 1 to infinity of a sub n is infinite, taking away a finite term and looking at the sum from n equals 2 to infinity of a sub n will not make that finite. You will still have an infinite sum. So these either converge together or they both diverge together. And that's going to be important in understanding how this test works. If we focus on the left side of our inequality, we can conclude that if the integral from 1 to infinity of f of x converges, so does our series, the sum from n equals 1 to infinity of a sub n. That's because if the integral itself is finite, then because the sum from n equals 2 to infinity of a sub n is smaller than it, it must also be finite. And because we know that when the sum from n equals 2 to infinity converges, so does the sum from n equals 1 to infinity, we can conclude that our series converges. If instead we focus on the right-hand side of our inequality, we get to draw a different conclusion. Here we know that if the integral diverges, then our series must diverge as well. That's because if the integral from 1 to infinity of f of x is infinite, given that the sum from n equals 1 to infinity of a sub n is larger than that, it must also be infinite and therefore does not converge. Putting these two ideas together gives us the statement of the integral test. If we want to know whether or not a series converges, we can compare it to the corresponding integral from 1 to infinity. And if we can determine the convergence or divergence of the integral, we can assume the same about the series. One word of caution in using the integral test. While we can use the value of the integral to help us determine whether or not the series converges, it is not the case that the value of the integral and the value of the series are the same in the case of convergence. For our first example, let's take a look at a series that you may be familiar with, the sum from n equals 1 to infinity of 1 over n. This is called the harmonic series. You might recall that when we look at this series and we attempt to use the divergence test, we found that that test was inconclusive. If we take the limit as n approaches infinity of 1 over n, we get 0. But in the case of the divergence test, that doesn't tell us anything. So what we want to do now is use the integral test. So our function here is going to be the function f of x equals 1 over x. And we know that for x greater than or equal to 1, this is continuous. It is positive. And it is decreasing. As x gets larger, 1 over x necessarily gets smaller. Therefore, we've satisfied the three conditions in which the integral test is a valid test to use. So we're going to explore the integral from 1 to infinity of 1 over x dx. Now, you may know something about this integral based on the p-test. We'll go ahead and work through the details. We know that this is the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And that is going to be equal to the limit as b goes to infinity of the natural log of x evaluated from 1 to b, which is the limit as b goes to infinity of the natural log of b minus the natural log of 1. the natural log of 1 is 0, but the natural log of b is unbounded, so that this limit is infinity. So in other words, the integral diverges. That tells us then that the sum from n equals 1 to infinity of 1 over n, the corresponding series, also diverges. We'll take a look now at a slightly different series. This one's going to involve natural logarithms. So we've got the sum from n equals 2 to infinity of 1 over n ln n. Notice that this series, or the sequence that the series is built on, is undefined when n equals 1 because the natural log of 1 is 0. So we need to start this at 2. So we're going to look at the function f of x equals 1 over x ln x as our corresponding function, and we're going to examine whether or not that integral converges. We need to make a convincing argument that our function is continuous, positive, and increasing, but since we're looking at values bigger than or equal to 2, that is certainly going to be the case for this function. Now, because our series is starting at 2, we can actually look at the integral from 2 to infinity of f of x dx, which is going to be the limit as b goes to infinity of the integral from 2 to b of 1 over x ln x dx. We can solve this using u substitution. We'll let u be ln x so that du is 1 over x dx. Rewriting our integral, we get the integral of 1 over u du. And our bounds change from 2 to b. When x is 2, we know that u is going to be the natural log of 2, and when x is b, u is going to be the natural log of b. And so I neglected to write my limit here. That's terrible form. We'll add that in, the limit as b goes to infinity. And that's going to be the antiderivative of 1 over u is natural log of u. So we have the limit as b goes to infinity of the natural log of u, evaluated from the natural log of 2 to the natural log of b. A little bit of a strange looking result. We have the limit as b goes to infinity of the natural log of b minus the natural log of 2. But we know that as b goes to infinity, its natural log becomes unbounded, and therefore the natural log of that value is also going to become unbounded. So we see once again we have an unbounded integral, which means that the series from n equals 2 to infinity of 1 over n natural log of n diverges. For our final example, we're going to examine the series from 3 to infinity of 1 over n ln of n squared. Now you may be asking yourself, isn't this very similar to what we just did? Aren't we going to get the same result? But if you think about it, natural log of n squared grows much more quickly than the natural log of n does, which means our denominator is getting bigger faster, and our entire series is getting smaller faster. So we may see a different result. Let's check out what happens. So again, we're going to use the function f of x equals 1 over x times the natural log of x squared as our function. For x greater than 1, this is going to be continuous, this is going to be positive, and this is going to be decreasing because the denominator is increasing. And so we can apply the integral test to this series. So if we look at this integral, because the series is going from 3 to infinity, let's also look at the integral from 3 to infinity of the function 1 over x ln of x all squared. We're going to set that up as the limit as b goes to infinity of the integral from 3 to b of 1 over x ln of x squared dx. And we're going to also use u substitution for this. So we'll let u be the natural log of x one more time. Du is equal to 1 over x dx. So if you're still thinking to yourself, how is this any different? I don't blame you, but hold on. We'll see what happens. So this is now the limit as b goes to infinity of the integral from the natural log of 3 to the natural log of b of 1 over u squared du. When we take that antiderivative, we get 1 over u. So we have the limit as b goes to infinity of negative 1 over u, evaluated from the natural log of 3 to the natural log of b. And so we get the limit as b goes to infinity of negative 1 over the natural log of b plus 1 over the natural log of 3. Well, as b goes to infinity, natural log of b also goes to infinity, which means our first term here is now going to 0, and this is exactly equal to 1 over the natural log of 3. So we now know that the integral from 3 to infinity of f of x dx converges. So the sum from n equals 3 to infinity of 1 over n natural log of n squared also converges. However, we don't know anything about the value of that series. All we know is that the series converges. We have a value for the integral, but we have not found a value for that series. So to wrap things up, if you have a function that corresponds to a sequence and that function is continuous, positive, and decreasing for values of x bigger than or equal to 1, then you know that when the integral converges, the corresponding series converges. When the integral diverges, the corresponding series also diverges. And one more gentle reminder that in the case of convergence, while we might be able to determine that the series converges, the value of the integral does not tell us anything about the value of the series.